Ever thought about why quantum physics is often called the theory of the small? Well, that's because it's all about the microcosm, the realm of particles far tinier than atoms. Quantum physics, my friends, is the gateway to a universe that's as fascinating as it is mind-boggling. Now, if you're a fan of predictability, brace yourself, because quantum physics is where things get whimsical, where the laws of classical physics take a back seat, and uncertainty rules the roost. You see, while classical physics lets us predict with precision how a thrown ball will arc through the air or how planets will orbit the sun, quantum physics is a different beast altogether. It tells us there's a probability of finding a particle here or there, but never a certainty. Let's delve deeper into the quantum realm. Imagine a particle that's not just in one place at one time, but in 2, 3, or 100 places simultaneously. Sounds like a sci-fi movie plot, doesn't it? But it's not. It's a fundamental principle of quantum physics known as quantum superposition. This concept suggests that a particle doesn't settle into one state or another until it's observed. It's like that age-old question: if a tree falls in a forest and no one is around to hear it, does it make a sound? In the quantum world, until someone decides to listen, the tree is both falling and not falling at the same time. And here's another mind-bender. A particle in superposition isn't just in multiple places at once, it's also spinning in different directions simultaneously. Until we observe it, it's spinning both clockwise and counterclockwise. Once we take a peek, it picks a direction. Seems bizarre, doesn't it? But that's just the beginning of the quantum world's oddities. Did you know that you can't simultaneously know the position and velocity of a particle with absolute certainty? This seemingly odd statement is the crux of what's known as Heisenberg's uncertainty principle, a fundamental concept in quantum physics that adds a layer of unpredictability to our understanding of the universe. Let's think about it this way. Imagine you're trying to catch a fast-moving ball. You can see where it is right now, and you can see how fast it's going, but you can't know both of these things with perfect precision at the same time. The faster the ball is moving, the harder it is to pin down its exact location. Conversely, if you're able to pinpoint its location, you're left with less certainty about its speed. This is the uncertainty principle in action. And while our ball analogy is a simplification, it helps to illustrate the strange reality of quantum particles. They don't behave like everyday objects we're familiar with. Instead, they exist in a state of fuzziness where their properties, like position and velocity, can't be precisely known at the same time. Heisenberg's uncertainty principle is more than just a quirky rule, though. It's a fundamental part of the framework of quantum mechanics, contributing to the theory's inherent unpredictability. Because we can't know everything about a quantum particle's state at once, we can only make predictions based on probabilities. It's a bit like trying to predict the weather. We can make educated guesses, but we can never be 100% sure. This principle also has profound implications for our understanding of reality itself. It suggests that at the quantum level, the universe isn't deterministic. That is, everything isn't just cause and effect. Instead, there's a certain amount of randomness built into the very fabric of reality. In the quantum realm, the more we know about where something is, the less we know about how fast it's moving, and vice versa. This is the fascinating and somewhat perplexing world of quantum physics, where certainty is replaced with probability, and where our everyday understanding of how the world works is turned on its head. Imagine if you could instantly know the state of an object millions of miles away. Quantum entanglement makes this possible. Welcome to the world of quantum entanglement, a phenomenon that Albert Einstein famously referred to as spooky action at a distance. So, what exactly is quantum entanglement? Well, it's a peculiar aspect of quantum theory where two particles become intertwined or entangled in such a way that they instantly reflect each other's state, no matter the distance between them. This means that if you measure one particle, you'll instantly know the state of its entangled partner. It's as if the two particles are communicating faster than light, which is a big no-no in Einstein's book. But remember, quantum physics plays by its own rules. Let's bring this concept to life with an analogy. Imagine you have two coins that are magically entangled. You place each coin in a box, and you take one box with you to the moon, leaving the other on Earth. Now, these are not ordinary coins. They'll always land on the same side when flipped, no matter how far apart they are. So, if your coin lands on heads on the moon, the coin on Earth will also be on heads, even though there's no physical connection between them. But here's where things get even weirder. Until you actually flip your coin, it exists in a superposition of states, meaning it's both heads and tails at the same time. Only when you flip the coin and observe the result does it choose a state. And at that exact moment, the coin on Earth also chooses a matching state. Quantum entanglement challenges our everyday experiences and notions of reality. It suggests that the universe is deeply interconnected, even across vast distances. It's an idea that has profound implications not only for physics, but potentially for fields like cryptography and computing as well. Quantum entanglement defies our understanding of space and time, making it a truly fascinating aspect of quantum physics. So as we continue to delve into the quantum world, be prepared to leave your intuition at the door, because in this realm, normal is anything but. What if I told you that a particle can pass through a barrier that it shouldn't be able to? Now, that sounds like a plot twist right out of a science fiction novel, doesn't it? But hold on to your hats, because this is the reality in the fascinating world of quantum physics. Let's dive into the concept of quantum tunneling. This phenomenon defies our everyday understanding of the world. It's something that would never happen according to the laws of classical physics. Let's imagine a ball rolling up a hill. According to the laws of gravity and energy conservation, if the ball doesn't have enough energy, it can't make it over the hill. It will roll back the way it came. This is a situation we're all familiar with, right? But in the quantum world, things are a bit different. Picture the same scenario, but this time, the ball represents a quantum particle and the hill is a barrier. Now, if the quantum particle doesn't have enough energy to cross the barrier, it doesn't just roll back. Instead, it can simply show up on the other side of the hill. It's as if the particle took a shortcut through the hill instead of going over it. This is quantum tunneling. How does this happen? Well, quantum physics tells us that particles also have wave-like properties, and these waves can extend beyond the barrier. So, even though the particle might not have enough energy to cross the barrier, a part of its wave can still make it to the other side. If this happens, the particle can suddenly appear there. Quantum tunneling is not just a theoretical idea, it's a real phenomenon that has been observed in the lab. It's also the principle behind many of our modern technologies, like the scanning tunneling microscope and flash memory in computers. So next time you're faced with an obstacle that seems insurmountable, remember the quantum particle. In the quantum world, barriers are merely suggestions, not strict boundaries. You might be wondering, why does all this quantum weirdness matter to me? Well, let's delve into the everyday impact of quantum physics. It's not just a concept that only affects particles in a lab. It's at work in many of the technologies we use daily. Take, for instance, the humble computer. The semiconductors at the heart of our computers and smartphones rely on quantum mechanics. Quantum physics explains how electrons move through these semiconductors, enabling us to manipulate electronic signals to produce the ones and zeros of digital information. And how about healthcare? Medical imaging technologies like magnetic resonance imaging or MRI scans are grounded in quantum physics. These scans use the principles of nuclear magnetic resonance, a quantum phenomenon, to create detailed images of the human body. Without quantum physics, we wouldn't be able to peer so deeply into the human body without resorting to invasive procedures. But the impact of quantum physics extends beyond what we already have. It's also shaping our future. Consider quantum computing, a field that's been making headlines recently. Quantum computers use the principles of quantum mechanics to process information in a fundamentally different way from classical computers. They promise to solve problems that are currently beyond the reach of even the most powerful supercomputers. And let's not forget about quantum teleportation. No, it's not about beaming humans from one place to another, Star Trek style. Rather, it's about transferring the state of a quantum particle from one place to another, without any physical movement of the particle itself. While still in its early stages, this technology has the potential to revolutionize communication and cryptography. So, while the quantum world may seem distant and strange, it's closer to our everyday lives than you might think. Quantum physics isn't just about understanding the universe at its most fundamental level. It's also about harnessing that understanding to improve our lives and drive forward technological progress.